Hey, I see you're back. You're doing well to come this far. We've got this presentation and one more, and that brings you up to a good standard in basic trigonometry. The Pearson's textbook, which I'm using the screen clippings from here today, is calling these problems 2D mixed problems, mixed two-dimensional problems. I'm going to call these problems in this presentation go-between problems. And you'll see in a minute why we might call them go-between problems or questions. And let's have a look at the first diagram down here, this one. Can you see that in this triangle here we want the angle theta? And can you see also that we only know 60? Find an angle by now. You should know that we need two sides, opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. And we don't have that. So I reckon we will need to find this side first. That's going to be our go-between side. It's going between two triangles. All right, this one down here, we can go into this triangle and work out that side and use it to go between the information we have in this triangle and help us out in the one above. So if you like, go between problems have two steps or phases. Work in one triangle, get some information, and that could be about a side or an angle, and then use it in another one, go between the two triangles. Let's have a look at this one down here now. This problem, we want to find x, which is the angle in the big triangle. So if we were to actually try and draw that big triangle, just coming here now, straight up there and down there, that big triangle has x there. It's got 70, but we only know this top bit is 20 metres. Hey! We want all of that side in the big triangle so that we can find x. And I think it's going to be sort of opposite and adjacent, isn't it? Well, what could we do? What's the go-between? This is the go-between side here. If we found that, we could go between the triangles, pop it over here, and we'd be in business. So the go-between is that side. Can we find it? Well, let's look. This triangle here has a 90, 58, 70. Oh, we can find that side because we have two pieces of information, an angle and a side. And we can find the other side and go between the two problems. That's what we're about here, being a little bit tricky in joining together the pieces of information that we've got, even though they might be in different triangles. Okay, let's go down and have a look at what Pearson say here. And here situations arise where one trig ratio is required to find unknown side or angle, and then we go on and use it. Here's an important point. If you're using calculations over and over again, don't keep rounding. The accumulation of errors due to rounding. So we use all the decimal places we can. Okay, don't round it off if you're finding a go-between side or angle. Keep all the figures there so you don't keep rounding it off and introduce inaccuracies. We only round off the final answer, so we'll write that down. Round off the final answer only. Final answer to the whole problem, not to the go-between side. All right, let's look at some typical problems now that are go-between problems. Find the value of x and y rounded to two decimal places. Okay, so there are two sides in this triangle that we need to find. And what's the go-between side? I think it's x here. I think x is the go-between, because here we see it, it belongs in this triangle here, where we can find x. What do? Go to the angle, look out, that's the opposite. Go to the 90, look out, that's a hypotenuse. And the other one is the adjacent. Then we list the information. Always the same process. I prefer you to actually put in Sokotoa at this stage. so that you can make the choice. Yes, I've got sine because it's opposite over hypotenuse. It's x over 24 is the sine of 41. This is going back to the beginning problems where we knew an angle and one side and we had to find the missing side. Do you remember? You multiply by 24 and get x. We're not going to round it. Why? Because now we have to use it as the go-between side to go into the next triangle. So let's draw the next triangle up. And we've got x now. Shouldn't put x there. We should have put that unrounded answer there. We don't want to round it off and lose accuracy yet. And then we have y and our angle. So we go in again. Look from the angle out, that's the opposite. Look out from the 90, that's a hypotenuse. Okay, so they've done that without doing that step. I think that's naughty. Should always go through the same steps. And then we go to Sokotoa to choose what we've got there. We've got the opposite and the hypotenuse, so we've got the sine of 19 is the x over the y, but x is this angle here and this side here, and so we could, they've rearranged it like that. I'd rather do it this way. Sine of 19 equals 15.745. You don't have to write it down, but just keep in mind what's happening. And then we multiply by y, and then finally divide by sine 19. So it becomes 15.74. Write all that in, divided by the sine of 19. So it's back to one of those other problems that we had from the very beginning. So x is the go-between side. It goes between an angle, a triangle where we can find it, and then it's useful in finding the final answer in the other triangle. So here, don't forget, we usually round off the side and the two sides there to 2 decimal places if that's what's asked for. Usually, if it's not stated, we would round to 3 significant figures. So that would be, this would be the answer now to 3 significant figures. Put that in brackets. Okay, so depending on what they ask for there. All right, do you want to do another one? Let's have a look. Another go-between problem. Thea cites 2 swimmers. Here we are, so this is her up here. I would rather call that T for Thea, but anyway, and she cites 2 swimmers at angles of depression, so she looks down, and so that's going to be equal to this one, isn't it? Alternate angles. Then she has to look further down to see the other one, and so that's going to be equal to that, alternate angles, remembering horizontal lines here are parallel. So what can we say? Well, we're trying to find the distance between the 2 swimmers, which is really this distance here. So what we will need to do is to draw working one triangle and then use it in the other, if we can there, as a go-between. So let's have a look at working in this first triangle here with x in it. So here it is drawn down here. Go to the angle, look out, that's the opposite. Go to the 90, look out, that's hypotenuse. So the other one is the adjacent. So then we write Sokotoa to work out here after we've stated the given information. And we see we have the opposite and the adjacent, so we use the tan of the angle is 40 over x, and then if you remember, you multiply by x and then divide by the tan of the angle, so we get this line, and so we have x unrounded as this distance. Now, is that going to actually help us? Let's see how we can draw the second triangle and work out how x is going between the two here. Here in the second triangle, we find that we do have enough information. Looking out, that's the opposite, that's the hypotenuse, therefore this one's the adjacent. Listing the information, right, then SOHCAHTOA, each time the same. So the opposite, what have we got? Opposite and adjacent, so it's the tan. And y is in the bottom line, so it's the same rearrangement. Multiply by y, let's just check that to get it out of the denominator. And then dividing by the tan of 3435. Okay, on the calculator it doesn't have degrees and minutes on the Casio there, so 35 minutes is 35 60ths of a degree. A minute is a 60th of a degree, so you can change that to a decimal equivalent and use that for tan of 34 point so many degrees. Okay, so we now have this side, and just remembering the problem, let's go back up. So we've now got this and this whole distance. So the actual distance we want is the distance between the swimmers. Okay, so we've got little x and little y, and the distance between the swimmers is one minus the other. No rounding yet, and then we round it at the end to two decimal places, or 30.2 metres to three significant figures. So then we state the answer. The distance between the swimmers is approximately 30.18 metres. You always use approximately because you have done some rounding. So that's another variation on the go-between ones, where you needed x because in the big triangle you had to take it away from that final length there. All right, let's have a look now at this comment. We're pretty heavily into trigonometry, but don't forget, sometimes it's useful to find a missing side just with Pythagoras, not with trigonometry. So just remember the square on the hypotenuse over here is equal to the sum of the squares on the other two sides. That could be helpful. So what are we talking about? We're talking about where you might have a side here which is 12 metres, this is 5 metres, and you know this angle, so you have a choice. You could use the angle and find this hypotenuse using trigonometry, but what might be easier is to say that the square on the hypotenuse is the sum of the squares on the other two sides and not use SOHCAHTOA, because SOHCAHTOA might actually be more working out, more calculator work than using Pythagoras. So this comes to, of course, I've chosen a Pythagorean triple here. This comes to 169, or 13, and it's only positive 13 because the side must be a positive. So don't forget, when you're doing go-between problems and you get into the second triangle and it's right-angled, you might find it easier to use Pythagoras to find that length. Okay, let's move on, do the final work example, and then you can have a go. So here's clearly a go-between problem, because you want x over here, and you can see x is in a right-angled triangle, but you've only got 40 degrees. So B will be the go-between. Go and find B first, and then use it in the second triangle. So V is the go-between side. So we could use here Pythagoras, couldn't we? We don't actually know an angle there or an angle there, so we have to use Pythagoras. which says, or Pythagoras said, square on the hypotenuse equals the sum of the squares on the other two sides. And when we do that, we should put Pythag in brackets. So then working that out, we get B is 55. And then we can come down and use it in the other triangle. So we now have that 55. Go to the angle, look out. We have the opposite, so that's the opposite. Go to the 90, that's the hypotenuse. That's what we'll want. We want the x there. So list them down. Angle is 40. So then write down Sokotoa so you don't make any mistakes. And you've got opposite and hypotenuse. So you can write the sine of 40 is 55 over x. And then, of course, the next step, x sine 40 equals 55 if you want, putting it in steps. And then x is 55 over sine of 40. And then we have that to 2 decimal places, or 85.6 to 3 significant figures. Okay. Now, the use of Pythagoras there is important, because here to actually use trigonometry in that go-between triangle, the first one there, we, if you remember, only used 70 and 73 and 48. So we could have used those to get the angle and then use trigonometry to come across here and get B. But as Pearson's is stating here, you would have had to do 2 lots of calculations. Get the angle and then use that to calculate B. So Pythagoras was quicker there. So you might think about that. If you have a right angle triangle and 2 sides in it, and you want the third side, it might be easier to go directly with Pythagoras. Let's have a look at Pearson's practice problems here for you. I've just gone through the worked example 16, so you might have a go now at question 1 and 2 there. The answers are right down the bottom. This time I haven't got them down the side, so I'll just move down there and show you, so that when you're ready you can go back to this spot in the presentation and pause it. So here they are here. There are the answers at the bottom. So just forward through and pause it there, mark your work, and then spin back. So let's go back now. So there are a lot of mixed problems here, all go between problems, where remember you'll find something in one triangle first and to then go across and need it or use it in the second triangle. Alright, so try and see which one to use first and so on. I think here important emphasis on getting a diagram, an accurate diagram. I don't know whether you'll have time to actually do all of these questions, so I'll just give you some at a time here to have a go and pause it there. And then maybe 4 and 5 and 6, something like that. Go down, have a look at your answers as you go. The understanding questions, a bit more complicated, starting at questions 7 through 9 there. Same idea. You'll pop in one triangle, find something, use it as a go-between in the next one. And there's plenty of problems if you've got time to do these. Come down to 10 here. So an interesting camping problem here. You see how you can use it to advantage in a practical sense. And then 12 is an interesting one. They help you here with the diagram, drawing a right angle triangle, pilot landing a plane here. See what you can do with that one. So as I stop it, pause it and have a go at some of these. If you could do all of them, that'd be good. And then the reasoning ones, a bit harder, an envelope one there, some hints over here, remember the hints, and then going on to 17 and the open-ended problems where you look for different possibilities and you can make up your own scenarios there. Okay, here's an interesting hint for this one here, because we have a polygon and the sum of the interior angles of an n-sided polygon is n take 2 times 180, because within an n-sided polygon we've got n take 2 triangles. So we've got n take 2 lots of 180 degrees internal angles, because the sum of angles in one triangle is 180. So then just coming down here, there are all the answers. So do as many as you can, mark your work. I think that's very, very important. And scroll back and forward so that you can do that. All right, so what are we going to do now? Well, you might have wondered, hey, my world's not flat, mate. It's three-dimensional. So can we actually use trigonometry in three-dimensional problems? And that's the last presentation. And I hope to see you then to do that interesting work. At the moment, work hard, enjoy yourself, and at the moment from me, it's cheers for now.